Let's continue. 2.3 Electromotive force and circuits. When we flip on the light switch on a wall and the circuit is completed, either AC or DC, the light bulb appears to glow immediately. But when we make a non-cellular telephone call, the electrical signal carry our voice travels through connecting wires at seemingly infinite speed. This signal is transmitted through the conductors at nearly the speed of light. And why is it so? Is it it is not the electrons that move at this speed, okay? Remember that. Although electrons inside metal at room temperature have an average speed of a few kilometers per hour, they make up no current because they are moving in all possible directions. There is no net flow in any preferred direction. But when a battery or generator is connected, an electric field is established inside the conductor. Battery is connected, an electric field is established inside the conductor. What is this? What does this mean? When we are establishing a current, we can produce an electric field inside this current. Okay? From this figure, we have this electric field inside the current when we are completing the circuit. Only then, okay, if this is not connected, there is no electric field produced inside. Electric field is imaginary. You cannot see it, but there is an, okay, as what I have said, it's like a gravity. We cannot see it, but we are here because of gravity. Just like in an electric circuit, there is an electric field generated when a circuit is in closed loop or complete. Now, where am I? Okay. When a battery or generator is connected, an electric field is established inside the conductor. The electrons continue their random motions while simultaneously being nudged by this field. It is the electric field that can travel through a circuit at nearly the speed of light. So, yung sa signal na nare-receive natin from a telephone, the voice will travel along with the electric field in a circuit, because electric field can travel to a circuit at nearly the speed of light. The conducting wire will act as a guide lang or a pipe for the electric field lines. In the space outside the wire, the electric field has a pattern determined by a location of electric charges, including charges in the wire. And inside the wire, the electric field is directing along the wire. So again, inside the wire, there's an electric field that is being guided in the conducting wire. Sa labas naman ng ating conducting wire, there is only a pattern. A pattern that can be determined by the location of electric charges. When you plug a lamp into an outlet, energy flows from the outlet into the lamp and not the electrons. Energy is carried by the pulsating electric field and causes vibratory motion of the electrons that already exist in the lamp filament. If a voltage of 120 volts is impressed on a lamp, then an average of 120 joules of energy is dissipated by each coulomb of charge that is made to vibrate. Most of this electrical energy appears as heat, while some transforms to light. Okay? Power utilities do not sell electrons. They sell energy. You supply the electrons by means of our conducting wires. We can supply the electrons. And for example, the Magelco or the Collat will supply the energy. When you are jolted by an electric shock, the electrons making up the current in your body, what are these electrons? For example, is yung ating salts, the sodium, the chloride, the magnesium, the ions that are present in our blood or in our body will make up our body possible na maka-receive ng electric shock because of our electrons. Electrons do not emerge from the wire and pass through your body and into the ground, but energy does. The energy simply causes free electrons already existing in your body to vibrate in unison. This is why you need to have an insulator or an insulation gloves kapag hahawak ka ng electricity current or electric wires. Kasi magiging conductor tayo ng electricity if we are in touch with the electric current or electric voltage. Small vibrations tingle, large vibrations can be fatal. In an electric circuit, there must be a device somewhere in the loop that acts as the water pump in a water fountain. In this device, a charge travels uphill from lower to higher potential energy, even though the electrostatic force is trying to push it from higher to lower potential energy. The direction of current in such a device is from lower to higher potential, just the opposite of what happens in an ordinary conductor. The influence that makes current flow from lower to high potential is called electromotive force, or abbreviated as EMF, pronounced as EMF. This is a poor term because EMF is not a force but an energy per unit charge quantity like potential. The SI unit of EMF is the same as that for potential. The volt. 1 volt is equals to 1 joule per coulomb. A typical flashlight battery has an EMF of 1.5 volt, and this means that the battery does 1.5 joules of work on every coulomb of charge that passes through it. Again, electromotive force, okay? Remember that in an electric circuit, the current will flow from high to low, but because of an electromotive force, from high to low, okay? High to low. But because of an electromotive force, the flow of current will become from low to high, okay? And this is why when we say a battery that has an EMF of 1.5 volt, this means that the battery does a 1.5 joules of work on every coulomb of charge. Ibig sabihin, yung ating battery will make the current in our charge, or the charge in our current passes from low to high instead of the typical high to low. Every complete circuit with a steady current must include some device that provides EMF. Such device is called a source of EMF. Batteries, electric generators, solar cells, thermocouples, and fuel cells are all examples of EMF. All such devices convert energy, some form mechanical, chemical, thermal, and so on, into electric potential energy and transfer it into the circuit to which the device is connected. An ideal source of EMF maintains a constant potential difference between its terminals, independent of the current though. We define electromotive force quantitatively as the magnitude of this potential difference, and the relationship between the potential difference, VAV, is equals to EMF is equals to IR. That is, when a positive charge Q flows around the circuit, the potential rises as it passes through the ideal source is numerically equal to the potential drop VAB. Okay, so this relationship applies to all. Once the EMF and the resistor R are known, this relationship determines the current in the circuit. So a voltage source is just always or equal to EMF, and that is also equal to IR. Kapag given ka ng resistance and given ka ng I, malalaman mo kung ilan ang current na nagpo-flow sa isang circuit. Real source of EMF in a circuit don't behave in exactly perfect path. The potential difference across a real source in a circuit is not equal to the EMF. The reason is that charge moving through the material of any real source encounters resistance. We call this the internal resistance of the source denoted by R. So, hindi lang big letter R, kundi may small letter r pa. Itong internal resistance is a real source, a real resistance that can be encountered in a moving charge. For example, is yung ating wire has a resistance, external resistance, and an internal resistance. If this resistance behaves according to Ohm's law, again, what is Ohm's law? V is equals to IR. Same as this equation. R is constant and independent of the current I. As the current moves through R, it experiences an associated drop in potential equal to IR. Okay? So, IR. Equal din siya kay IR. Thus, when the current is flowing through a source from negative terminal B to the positive terminal A, the potential difference between these terminals is equals to this one. VAB is equals to EMF minus IR. Why is it naging ganyan? Because they are all equal. IR in here, when you move it as in the mathematical law, implies when you move it from this positive form, between this equal, magiging from positive, magiging negative siya. Okay? Magiging ganyan siya, minus IR. Okay? So, VAB is equals to EMF minus IR. And since we're talking about internal resistance in here, instead na big letter R, ginamit is small letter r. Now, the potential difference VAB, called the terminal voltage, is less than EMF. Okay? So, in reality, VAB is always equal or less than the EMF. Because of the internal resistance, yung ideally, they are equal, but because of the internal resistance, si EMF ay magkakaroon ng minus small increment of resistance. That is why VAB is not equal to EMF in reality. So, a 1.5 battery has an EMF of 1.5 volt. Okay? But the terminal VAB of the battery is equal to 1.5 volt only if no current is flowing through it. Okay? No current. Ibig sabihin kapag no current, VAB is always equal to A. Kasi si current natin will become 0. Okay? Pero pag meron na siyang current, magkakaroon ng 2.2 will imply, and if the battery is part of a complete circuit through which current is flowing, the terminal voltage will be less than 1.5 volt. For a real source of EMF, the terminal voltage equals the EMF only if no current is flowing through the source. Remember that. Thus, We can describe the behavior of a source in terms of two patterns, or two properties. An EMF, which supplies a constant potential difference independent of current in a series with an internal resistance R. The current in the external circuit connected to the source terminals A and B is still determined by the Ohm's law. Combining these equations with 2.2, we find that VAB is equals to EMF minus the current and the internal resistance is equals to IR, or the current is simply equal to EMF over the resistance, the sum of resistance R and small r. That is, the current equals the EMF, again, divided by the total circuit resistance. So this term in here is a total circuit resistance. An important part of analyzing any electric circuit is drawing a schematic circuit diagram. Table 2.4 shows the usual symbols used in circuit diagrams. We will use these symbols extensively in this lesson and the next. We usually assume that the wires that connect the various elements of circuit have negligible resistance. From V is equals to IR, the potential difference between the ends of such a wire is 0. Table 2.4 includes 2 meters that are used to measure the properties of circuits. Idealized meters do not disturb the circuit in which they are connected. A voltmeter measures the potential difference between its terminals. An idealized voltmeter has infinitely large resistance and measures potential difference without having any current diverted through it. An ammeter, on the other hand, measures the current passing through it. An idealized ammeter has zero resistance and has no potential difference between its terminals. Because meters act as part of the circuit in which they are connected, these properties are important to remember. We will talk all about voltmeter and ammeter in the next, so please let's focus on this table 2.2 symbols of circuit diagrams. A conductor with negligible resistance will always be a straight line. When there's a resistor, the resistor is just like this. Source of EMF is a positive and negative terminal that has a sign E in here. Source of EMF with internal resistance R can be placed on either side. So if there's an internal resistance, meron siyang highlight. Okay? Longer vertical line always represents the positive terminal. Longer vertical line is always the positive terminal and usually the higher potential. So the longer is the positive and the shorter is the negative terminal. So again, voltmeter and this symbol and ammeter and this symbol. Conceptual learning, activity 2.2, a source in an open circuit. Open, when we say open, it is not a complete circuit, rather an incomplete circuit. Figure below shows a source battery with an EMF E is equals to 12 volt and internal resistance R, 2 ohms. So in this symbol, it is an EMF with an internal resistance R. The wires to the left of the EMF and to the right of the ammeter, the wires to the left of and to the right of the ammeter, this is the ammeter A, are not connected to anything. So it is an incomplete circuit. Determine the respective readings VAB. So this is a voltmeter and the current I of the idealized voltmeter and the idealized ammeter. So there's an voltmeter connected in this wire, in this EMF wire, and an ammeter connected outside this EMF. For the solution, there is a zero current because there is no complete circuit. Our idealized voltmeter has an infinitely large resistance, so no current flows through it. Idealized, ha? If we say idealized voltmeter, it has an infinitely large resistance. If it has a very large resistance, very high, let's say infinite, see, current natin will become not important or magiging assuming na wala. Okay? No current flows through it. Hence, the ammeter reads is 0. Because there is no current through the battery, no current, there is no potential difference across its internal resistance. Okay? So, when we have current equals to 0, the potential difference is equal to the EMF. That is equal to 12 volt. And the terminal voltage of a real non-ideal equals the EMF only if there is no current flowing through the source, as in this example. For a complete circuit, on the other hand, we add a 4 ohm resistor to the battery in conceptual learning activity 2.4, forming a complete circuit in the figure below. So from this figure, we are to form a complete circuit na. What are the voltmeter and ammeter readings, VAB and current now? So from this circuit in the previous problem, we have now a complete circuit na mayroong resistor na 4 ohm. This is a resistor. And the current will flow from the positive terminal to the negative terminal. Okay? So, ang nadagdag lang is ang R. Our target variables are the current to the circuit A, A prime, B prime, B. So, the current in this circuit and the potential difference VAB, this one. The potential difference in this terminal A and terminal B. We first find the current by using 2.13 to find the VAB. We can use either equation 2.9 or 2.13, but here we use 2.13. The ideal ammeter has zero resistance, so the total resistance external to the source is just R. From equation 2.13, the current through the circuit A prime, B prime, B is then the EMF over the R plus the internal resistance R. That is 12 over 6 is equals to 2. And the voltage over ohmmeter is equals to ampere. Our idealized conducting wires and the idealized ammeter have zero resistance, so there is no potential difference between points A and A prime, or between points B and B prime. That is, VAB and VA prime B prime. We find that VAB by considering the terminal A and B only. In this figure, the terminal VAB in this terminal AB only, meaning to say this only. So, from Ohm's law, equation 2.9, VAB is equals to IR. The current is 2 ampere and the R is 4 ohms. That is equals to 8 volt. Alternatively, we can consider A and B as the terminals of the source, which is VAB alternatively is equals to EMF minus IR. So, EMF natin is 12 voltage. I natin is 2 ampere and the internal resistance R is 2 ohm. That is 8 volt. Either way, we see that the voltmeter reading is always 8 volts. As an evaluation, with current flowing through the source, the terminal voltage VAB is less than the EMF. The smaller the internal resistance, the less the difference between VAB and E. So, since, okay, napansin nyo? Sorry. VAB now is equals to 8 volt compare sa EMF na 12 volt. Dahil nga ito ay complete circuit. Hindi na siya equal. They are no more equal. Kasi ito is 8 volt sa complete circuit. Ito is 12 volt. But if it is not a complete circuit, they are always equal. As from the previous example natin. Okay. Now, learning activity 2.6. A source with a short circuit. In the circuit of learning activity 2.5, we replace the 4 ohm resistor with a 0 resistance conductor. What are the ammeter readings now? The ammeter readings. When we say, what are the meter readings now? The ammeter and the voltage readings. From the sketch below, our target variables are again current and the voltage source. There is now a 0 resistance spot between points A and B through the lower loop. So the potential difference between these points must be 0. Okay? So R now is 0. We must have VAB is equals to IR, and since 0 resistance, there is no voltage difference in here. So 0, no matter what the current, we can therefore find that current I from equation 2.13, I is equals to E over R. So the current I will only be now dependent on the internal resistance R, small r. So 12 over 2 is equals to 6 ampere. As an evaluation, the current has a different value than in example 2.5 kasi sa 2.5 it is 8 ampere. Even though the same battery is used, the current depends on both the terminal resistance R and the resistance of the external circuit, big letter R. The situation here is called a short circuit. Short circuit. The external circuit resistance is 0 because terminals of battery are connected directly to each other, and the short circuit current is equal to the EMF divided by the internal resistance R. And warning, short circuits can be dangerous. An automobile battery or a household power line has a very small internal resistance, and the short circuit current can be great enough to melt a small wire or cause a storage battery to explode. Okay?